Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals, and in this session we are going to discuss this integral where we have to find out the value of this important definite integral from 0 to 47 pi over 2, and the integrand is the square root of 1 minus cosine 4x, and here we have dx. So let us first call this integral as I. Right now, here in order to evaluate this integral, we have to make use of some important concepts from trigonometry, and then from absolute value function, and then from some important property of definite integrals involving periodic functions, right? So let us see the concepts one by one, and let us see how easily we can find out the value of this definite integral. So let us start with trigonometry, right? Now see, we know this important identity, that is cosine 2 theta is given by 1 minus 2 sine square theta, right? Now see, if we replace this theta by say 2x, then here we'll get 2 times 2x, that is cos 4x, and here we have cos 4x. So cosine 4x is 1 minus 2 sine square theta. Theta is 2x, right? So now rearranging the terms, we can now write 2 sine square 2x is equal to 1 minus cosine 4x. So we can now replace 1 minus cosine 4x by 2 sine square 2x, right? So now this integral takes the form 0 to 47 pi over 2, and here we have a square root of 2 sine square 2x dx, right? Now taking square root of 2 outside the integral, we have square root of 2, then we have 0 to 47 pi over 2, and here we have square root of sine square 2x dx, right? Okay, so now let us make use of the definition of absolute value function. Now see, the absolute value function is defined like this, that is mod of p is equal to square root of p square, right? And further we write mod of p is equal to a positive p whenever p is greater than 0, mod of p is equal to 0 whenever p is equal to 0, and mod of p is negative p when p is less than 0, right? So here we have square root of sine square 2x. So let us here replace this p by sine 2x. So mod of sine 2x is equal to square root of sine square 2x. So let us replace square root of sine square 2x by mod sine 2x. So now our integral, it assumes the form that is the square root of 2, and limits are from 0 to 47 pi over 2, and here we have mod of sine 2x, and here we have dx. Now let us utilize the concept of periodic function, right? Now see, the period of sine 2x is given by 2 pi over 2, that is equal to pi, right? But here we have a mod of sine 2x, right? So the period of mod of sine 2x is given by pi over 2, because we know that the period of mod sine x is given by pi, right? And when we have a mod of sine say ax, then the period of mod of sine ax is given by pi over mod of a, right? So if we compare here a mod of sine 2x with mod of sine ax, then we can see that the value of a is 2, right? So the period of mod of sine 2x is given by pi over mod of 2, that is simply equal to pi over 2, right? So here we conclude that the period of mod sine 2x is given by pi over 2. And now in this integral, we can see that in the upper limit, we have this period pi over 2, because here the upper limit is 47 pi over 2, right? So we can also write this integral as square root of 2, then we have 0, then we can write 47 times pi over 2. Pi over 2 is the period of mod sine 2x, and here we have mod of sine 2x dx. Now let us make use of an important property of definite integrals involving periodic functions, right? Now see, if we have an integral that is from 0 to say m times t, and here we have a periodic function f of x whose period is t, and m is some positive integer, right? Then the value of this integral is given by m times the integral from 0 to t, and here we have f of x dx. So this property is going to be very important in involving in solving this integral, right? And if we compare this integral with this one, then here we have 0, here also we have 0, and here the upper limit is 47 pi over 2, and this is equal to m times t. So if we compare both the sides, then t is pi by 2, which is the period of mod of sine 2x, and m is 47, which is a positive integer, right? And obviously here this periodic function f of x is given by a mod of sine 2x, right? Okay, so now the value of this integral is now given by this expression. So the value of I is now equal to square root and square root of 2, and here the value of m is 47. So we have m, that is 47, and then we have the integral from 0 to t. T is pi by 2, and f of x is a mod of sine 2x, right? So now the value of I is 47 root 2, and here we have 0 to pi by 2. This is mod sine 2x dx. So now we have to find out the value of this integral, right? And here the limits of integration vary from 0 to pi by 2, and here we have mod of sine 2x, right? So let us see here the concept of sign convention of trigonometric function in 4 quadrants, right? Because the sign convention it helps us to evaluate this integral, right? Now see here the value of x vary from 0 to pi by 2, right? And here we have sine of 2x. So if we multiply this inequality throughout by 2, here we get 0, and here we have 2x, and here this 2 and this 2 get cancelled, so we are left with only pi, right? So when x vary from 0 to pi by 2, then 2x vary from 0 to pi, right? And if we draw the quadrants here, here we have 0, here we have pi by 2, here we have pi, this is 3 pi by 2, and this is 2 pi, right? So 2x vary from 0 to pi. So it means we have to restrict ourselves to the first and second quadrant only, and these are the third and fourth quadrant. So the value of 2x vary from 0 to pi, and we have to confine ourselves to the first and the second quadrant only. And in the first and second quadrant, the sine function is positive, right? So a mod of sine 2x is equal to positive sine 2x when 2x belongs to the interval that is 0 to pi, as we have proved over here. So sine function is positive in the first and second quadrant, right? So now this integral I takes the form 47 root 2, and we have 0 to pi by 2, and mod of sine 2x is given by positive sine 2x dx. So now we have an easy integral here, and we know that integral sine say ax dx is given by minus 1 over a cos of ax. And here we have I is equal to 47 root 2, and the integral of sine 2x is given by minus 1 over 2 cos of 2x, and the limits of integration are from 0 to pi by 2. Now taking minus half outside the bracket, so we have minus 47 root 2 over 2, and we have simply cos 2x from 0 to pi by 2. Now substituting the limits and taking the difference, we have cos. First we have 2 times pi by 2, this pi by 2, then we have minus cos 2 times 0, and this is minus 47 root 2 over 2. This 2 and this 2 get cancelled, so we have cos pi minus cos of 0. So now cos pi is given by minus 1. So we have here minus 1, cos 0 is 1. So this is minus 47 root 2 over 2 times minus 2. Minus 1 and minus 1 becomes minus 2. So minus and minus becomes positive, and here this 2 and this 2 get cancelled. So we are left with only 47 times square root of 2, right? So viewers, the value of this integral is given by 47 times square root of 2. Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals. And in this session we are going to discuss this integral involving the fractional part function. So we have to evaluate this integral in which the lower limit is minus 7 by 4 and the upper limit is 6, and the integrand is the fractional part of 4x, right? So here let us first call this integral as I, right? So to evaluate this integral, we have to make use of some important concepts from functions, right? And moreover we'll also utilize the concept of periodicity of fractional part function, right? So let us see how easily we can solve this integral using the concept of functions and the concept of periodic functions. Now let us first quickly see the definition of fractional part function, and we know that if we have a function, say y is equal to f of x, that is equal to fractional part of x, then fractional part of x is defined as the difference of x and greatest integer of x, right? So this is the definition of fractional part function, and we know that the period of fractional part function is equal to 1, so we can write the period t as equal to 1, right? Okay, Now see, here we have this function that is the fractional part of 4x, right? So if we take this function as the g of x, that is fractional part of 4x, then the period of g of x is given by say t1, then t1 is given by t by 4, because here we have the coefficient 4, right? And we know that if we have the function say f of x and its period is t, then the period of f of say ax is given by uh, t by a, right? And here we write modulus of a. So if the period of f of x is t, then the period of f of ax is given by t divided by the absolute value of a, and here a is not equal to 0. Now see, for example, we know that the period of sine x is given by 2 pi, then the period of say sine 4x is given by 2 pi divided by a mod of 4. So here we have the coefficient that is 4. So the period of sine 4x is given by 2 pi over 4, that is pi over 2, right? So this concept is utilized here. The period of fractional part of x is 1, and the period of fractional part of 4x is given by 1 divided by the absolute value of 4, and that is simply a t over 4, and t is 1, so we have the period of g of x as 1 over 4. So in general we can say that the period of fractional part of ax is given by t divided by a mod of a, and t is 1, so we have 1 over mod of a, and a is not equal to 0. So now let us write this integral I as integral from minus 7 over 4, and here we have 6, and fractional part of 4x can be written as g of x, right? Now let us rewrite the limits in the form that is minus 7 over 4 can be written as minus 7 times 1 over 4, because 1 over 4 is the period of g of x, and here we have 6, so let us write 6 as 24 times 1 over 4. So we have now expressed the limits in this form. Minus 7 by 4 can be written as minus 7 times 1 over 4, and 6 can be written as 24 times 1 over 4, so that here we have the period of this function g of x, right? So now here we will utilize the an important property of definite integrals involving the periodicity of functions. Now see, we know this property, that is, if we have here p times t, and here we have q times t, and here we have a function say g of x, right? And p and q are some integers, and t is the period of this function g of x. So this integral can be written as q minus p, that is difference of these two integers, times the integral that is 0 to t, and here we have g of x dx. So now if we compare this integral with this one, then here the value of p is 7 minus 7, right? And the value of q is 24, and t is 1 by 4. So p is minus 7, q is 24, and t is 1 over 4, right? So here this integral, that is I is now equal to q minus p, that is 24 minus minus 7, and here we have 0 to t. T is the period of g of x, and for t we can write 1 by 4, and for g of x we can write a fractional part of 4x, and here we have dx. Now this is 24 plus 7, because minus and minus becomes plus, and this is 31. So here we have 31 times 0 to 1 by 4, and fractional part of 4x can be expressed using the definition of fractional part of 4x. So here for x we can write 4x. So fractional part of 4x is now equal to 4x minus greatest integer of 4x, right? So now we have to evaluate this integral, and let us first concentrate on this term. Now see, here the limits of integration vary from 0 to 1 by 4, and x lies between 0 and 1 by 4, right? So x lies between 0 and 1 by 4, and if we multiply this inequality throughout by 4, then here we have 0 times 4 is 0, and here we have 4x, and here 4 and 4 get cancelled, so we are left with 1, right? So this inequality suggests that 4x it lies between 0 and 1. So what we have done here, the limits of integration vary from 0 to 1 by 4. So x lies between 0 and 1 by 4. So if we multiply this inequality throughout by 4, then we get this inequality, and this inequality claims that 4x lies between 0 and 1. So by the definition of greatest integer function, anything lying between 0 and 1, the greatest integer of that term should be equal to 0. So here this term is equal to 0. So now we are left with 31, and here we have 0 to 1 by 4, and here we have 4x minus 0, because greatest integer of 4x is 0. So we have simply 4x, and here we have dx. Now we can take 4 outside the integral, so we have 31 times 4, and we have 0 to 1 by 4 x dx, and this is 31 times 4. The integral x dx is x square over 2, and the limits are from 0 to 1 by 4. So the value of this integral I can now be written as 31 times 4, and we can now substitute the limits, and we can take the difference. So when we take x is equal to 1 by 4, here we have 1 over 16, because this is x square, and here the denominator is 2, and when we take 0, this term is 0, so here we have 0, right? So now we can solve it. 31 times 4, then we have 1 over 16 times 2, so this is 4 times 4 16. So here we have 4 times 2 8. So the value of this integral I is equal to 31 over 8, right? So viewers, this is how we can find out the value of this integral using the concept of fractional part function and the periodicity of fractional part function.